In the last section, we briefly introduced carbon-13 NMR. In this section, we are going to talk about proton NMR. Proton NMR is much more sensitive than carbon-13 and gives us more information than carbon-13 NMR. Here shows some information proton NMR can give us. How many types of hydrogen atoms in a molecule? How many hydrogen atoms in each type? And how many hydrogen atoms close to each other? And we are going to discuss each of them in detail. First, let's go over different types of hydrogens. When two hydrogens are in identical environment, they will give the same NMR signal, and they are called homotopic. Let's take this molecule as an example. Our intuition tells us that these three hydrogens should in the same environment, and these three are also in the same environment, so they are equivalent. In fact, all these 6 hydrogens are equivalent, and they should give the same NMR signal, so only one signal for all 6 hydrogens. Formally, we can test homotopic hydrogens by replacing each with an X. X can represent any atom. Okay, for example, let's replace this hydrogen by X, and this is the molecule. Okay, if we replace this hydrogen by X, okay, we get a molecule like this. All right, so one X is here, one X is here, but remember this bond can rotate, and therefore this represents the same molecule. All right, so by replacing hydrogen by X, we get a same molecule, and therefore these 2 hydrogens are homotopic. On the other hand, if we replace these 2 hydrogens by X, we get 2 different molecules. One has an X attached to number 1 carbon, and the other one attached to 2nd carbon. So these 2 are isomers. They are different molecules, and therefore these 2 hydrogens are in different environment, and they give different NMR signal. And these 2 hydrogens are called unrelated hydrogens. If 2 hydrogens are attached to a same carbon that has 2 different substituents, in this case a methyl and ethyl, these 2 hydrogens are called enantiotopic. This is because when each of these hydrogens are replaced by X, you get 2 molecules that are enantiomers. Remember, in Organic 1, you learned that when a carbon has 4 different substituents, so A, B, C, D, this molecule is chiral, and this is called a chirality center. So this carbon is a chirality center because you have a ethyl, methyl, X, H. So this molecule is chiral. A chiral molecule has a mirror image that cannot be superimposed. They are different molecules, and they are called enantiomers. Okay, because these 2 are enantiomers, so the 2 hydrogens are called enantiotopic. Interestingly, enantiotopic hydrogens give the same NMR signal, unless the molecule is a chiral molecule. We're going to see in the next slide. In the last slide, we show that when 2 hydrogens are attached to a carbon that has 2 different substituents, these 2 hydrogens may be enantiotopic, because by replacing these 2 hydrogens by X, you get 2 enantiomers. On the other hand, if this molecule is already a chiral molecule, then these 2 hydrogens are called diastereotopic. Note that this carbon is a chiral center. It attached to 4 different substituents: a hydrogen, hydroxide, methyl, and an ethyl. Okay, this chiral center has a R configuration. By replacing these 2 hydrogens by X, you get 2 molecules. The chiral center is still R, unchanged. Okay, but this carbon becomes a chiral center. If one is R, the other one must be S. And these 2 molecules are not in mirror image. Even though R and S are mirror image, RR is not. So the whole molecule, they are not mirror image. Okay, when 2 isomers are not mirror image, they are not enantiomers. They are called diastereoisomers. And therefore, these 2 hydrogens are called diastereotopic. Interestingly, diastereotopic hydrogens have different NMR absorption. In summary, we have learned 4 types of hydrogens. Homotopic hydrogens are the hydrogens are in identical environments, and they give you only 1 absorption in NMR spectrum. Unrelated hydrogens are non-equivalent hydrogens, and they give you different absorption in NMR spectrum. Enantiotopic hydrogens are the hydrogens that when you replace by X, you give you enantiomers. Okay, and they still absorption at the same frequency. Diastereotopic hydrogens are similar to enantiotopic hydrogens. The difference is the molecule already have a chiral center, and these 2 hydrogens are diastereotopic, and they give you different absorption in NMR spectrum. Now, many people are confused with enantiotopic, diastereotopic. Okay, one way, simple way, is to look at 2 hydrogen attached to same carbon, and look at the molecule. If the molecule is non-chiral, then these 2 hydrogen is enantiotopic, and they have the same absorption frequency. If the molecule somewhere has a chiral center, then these 2 hydrogens are diastereotopic, and they give you different absorption frequencies. Similar to carbon-13, several major factors account for the resonance positions of most protons. Number 1 is deshielding by electronegative elements. You may remember, shielding effect is due to the electron clouds close to a nucleus. When an external magnetic field is applied, the motion of electron clouds induce a magnetic field oppose the applied field. The nucleus is shielded by the electron cloud from the applied magnetic field, and therefore a stronger magnetic field is needed for the resonance to occur. On the NMR spectrum, the chemical shift needs a high field. Okay, go to the right side, a high field side. If a electronegative element such as oxygen is added to the molecule, it will take part of the electron clouds away from the nucleus, and the nucleus is deshielded, and a low field is needed for the resonance to occur. So on the NMR spectrum is towards the left side, or low field side. Okay, so this is called the deshielding effect. Number 2 is anisotropic fields, okay, usually due to the pi-bonded electrons in the molecule, which will be discussed next. This table shows the deshielding effect of electronegative atoms. The hydrogen on methane has a chemical shift 0.23. When one of the hydrogen is replaced by iodine, the chemical shift goes to 2.16. So increased chemical shift. In the spectrum, it goes to the left side. So 0.23 goes to 2.16. When iodine is replaced by bromine, which has a higher electronegativity, the chemical shift goes to 2.68. Okay, that's 2.68. And when the bromine replaced by chlorine and then or oxygen or fluorine, the electronegativity increase and the chemical shift also increase. And on the spectrum, it go to the low field side or down field side. In a pi-bonded molecule such as benzene, these pi electrons can circulate, forms ring current, and the ring current cause induced magnetic field oppose the applied magnetic field inside the molecule, and the induced magnetic field is parallel to the applied magnetic field outside the molecule. And this has a shielding effect for the hydrogens inside the molecule, but deshielding effect on the hydrogens outside the molecule. And this is called the anisotropic effect. So for the hydrogens outside the molecule, it's like electronegative atoms attach to the molecule. The chemical shift go towards the left side or downfield side. Here shows the chemical shift trend for protons. Proton signal range usually from 0 to 10, which is much smaller than carbon-13. Protons attached to sp3 carbon have higher field strength. In the spectrum is towards the right side or high field side. Hydrogens attached to sp2 hybridized carbon is to the left side or downfield side. Hydrogens attached to carbon with no electronegative atoms have range usually 0 to 1.5. When electronegative atoms such as oxygen, nitrogen, halogens are attached, the hydrogen range from 2.5 to 4.5. Hydrogens directly attached to a double bond range from 4.5 to 6.5. Aromatic hydrogens range from 6.5 to 8. Aldehyde hydrogen in the range 10 to 12, just like carbon-13 is most downfield side. Here shows some typical chemical shifts in proton NMR spectroscopy. Sample question. This molecule shows 2 peaks in proton NMR spectrum. What are their approximate chemical shifts? First, draw the structure. Again, when you see CO2 in an organic molecule, that indicates a CO double bond with a CO single bond. And the CH3 with a 3 here indicates this carbon connect to 3 CH3. So it is C connect to 3 CH3. So here is the structure of the molecule. And the first thing you recognize, you have CH3, CH3, CH3 are all equivalent. So 9 hydrogens, they all appear at a single peak. And because they connect to carbon, not an electron withdrawing group, and therefore the range should be 0 to 1.5. Okay, the most upfield or the right side in the spectrum. So we assign 1.0 to all these hydrogens, 9 hydrogens. Now this CH3 connect to an electron withdrawing group or electronegative atom. So the range should be around 2.5 to 4.5. Now for oxygen, it's usually around 3.5 to 4. Okay, so so here is the actual spectrum, and you can see you have 2 peaks. One is about 3.5, and that is this one attached to oxygen, and the other one is around 1.5, 1.0 to 1.5, and that's these 9 hydrogens. Also note that the intensity of this hydrogen is much higher than this one. All right, so It's about 3 times intensity, and this is because the number of hydrogens here with this one, the ratio is about 9 to 3, so 3/1. In other words, the intensity of these two hydrogens also tells you the relative number of hydrogens of these two types of hydrogens. And that's another topic we're going to talk about next. In the last slide, we show that in an NMR spectrum, the number of absorption peaks tells us how many types of hydrogens in a molecule. In this case, we have 2 absorption peaks. That indicates we have 2 types of hydrogens in this molecule. The location of these absorption peaks tells us what types of hydrogens they are. A peak at 2.3, around 3.5, indicates a hydrogen connected to a carbon that is connected to an electronegative oxygen. A absorption peak at 1.2, around from 0 to 1.5, indicates hydrogen connected to carbon that is not connected to any electronegative atom. Additionally, the intensity of these absorption peaks tells us the relative number of hydrogens of each type of hydrogens. So the intensity is measured by integration. So this curve represents integration. This ratio of this integration is 3:1. That tells us that the ratio of type 2 and the ratio of type 2,1 is 3:1, number of hydrogens. We just discussed the number of signals and their locations, their intensity. And next we're going to talk about is the splitting pattern, the multiplicity. How many hydrogen atoms close to each other? The proton NMR peaks are often split into multiple peaks due to interaction between non-equivalent protons on adjacent carbons, called spin-spin splitting. The splitting obeys n+1 rule, which will be explained soon. The relative intensities are proportional to a binomial distribution. The set of peaks is a multiplet, and which is called doublet, triplet, quartet, etc. Here shows an example. Dichloroethane molecule contains 2 types of hydrogens marked by different colors, and we expect this molecule will show 2 different absorption peaks in proton NMR spectrum. The pink hydrogen connects to a carbon with electronegative atom. Usually the range is from 2.5 to 4.5. Now because we have 2 chlorine, and therefore it's probably greater than 4.5, perhaps 5.5 ppm. The red hydrogen connects to carbon with no electronegative atom, and usually from 0 to 1.5. And because of the 2 chlorine close to the carbon, so we would expect it's probably a little greater than 1.5. The actual NMR shows 2 absorption peaks, and one is around 6.0 and the other one is at 2.0, and that is what we expected. In addition, the intensity of the red one, okay, the first one due to the red hydrogen, is about 3 times of the one due to the pink one, and that's also as expected. Now there's one thing that looks strange, and that is those peaks doesn't look simple peaks. If we enlarge them, okay, you will see the one at 6.0 has 4 lines, which is called a quartet, and the one at about 2.0 has 2 lines, which is called a doublet. What caused this splitting? We're going to explain in the next slide. Let's first explain the N+1 rule. If we want to know the pattern of this hydrogen connected to chlorine, we look at the neighboring carbon and see how many hydrogens there. Since here we have 3 hydrogens, according to N+1, 3 plus 1 is 4, and therefore we see a quartet. And this quartet is for this hydrogen that connect to the carbon with chlorine, not 3 hydrogens, all right, but the hydrogen connect to the carbon with 2 chlorine. If we want to see the pattern of these 3 hydrogens, we look at the carbon, neighboring carbon, that how many hydrogens. And because we only see 1 hydrogen, and therefore according to N+1, 1 plus 1 is 2, and therefore these 3 hydrogen give you a doublet. Okay, therefore when we want to know the pattern of a certain hydrogen, we look at the number of hydrogens connect to the neighboring carbon. All right, if the neighboring carbon has 0 hydrogen, then it will show a singlet. If your neighboring carbon has 2 hydrogen, 1 hydrogen, it will give you a doublet. 2 hydrogen give you triplet, 3 give you quartet, 4 give you quintet, 5 sextet, 6 septet. Let's now explain why the 3 hydrogens appear as a doublet. Now, when a magnetic field is applied to the system, the hydrogen experience magnetic field not only due to the applied field, but also due to the local environment. Since a neighboring carbon has 1 hydrogen, and each hydrogen has 2 orientation, spin up, spin down. So the 2 orientation give these 3 hydrogens 2 different types of local environment. And because they have 2 different environment, they give you 2 absorptions. That's a doublet. Suppose this is the absorption line due to these 3 hydrogens when there's no hydrogen attached to a neighboring carbon. Now when the hydrogen is added, the hydrogen has 2 orientation or spin state, spin up, spin down. So now the absorption split into 2 lines. One is due to one of the 2 states, spin state, that reinforce the applied magnetic field, and the other one is due to the one of the 2 states opposes the applied field. Let's look at this hydrogen. Why does this hydrogen appear as a quartet? This is because the neighboring carbon has 3 hydrogens. Each hydrogen has 2 orientation or spin state. The combination of all these spin state give you 4 local environment, and therefore this hydrogen will have 4 absorption peaks. Let's look at the possible combinations of the spin state for the 3 hydrogens. There are 8 combinations of the nuclear spins for these 3 protons. One is all of them are spin up. So this first hydrogen spin up, second hydrogen spin up, third hydrogen spin up. Or 2 of them spin up, 1 spin down. And these have 3 possible arrangement. The first one is down, second and the third up. Or the second one is down, first and the third one up. Or the third one down, first and second up. That's 3 possible arrangement. All right. Another possibility is 1 up, 2 down, and that's also give you 3 arrangements: first up, second up, or third up. The last possible combination is all 3 protons are spin down. So 8 possible combinations, but only 4 effects on the hydrogen. Okay, all up, all down, 2 up, 1 down, 2 down, 1 up. All right, so that gives you 4 effects and therefore 4 absorptions. Okay, the intensity is 1, 3, 3, 1. Again, this is the absorption line due to the green hydrogen when there's no hydrogen attached to the neighboring carbon. And now when these 3 hydrogens are attached to the molecule, the spin combination gives you 4 effects on the applied magnetic field, cause the absorption to split into 4 absorptions, and the intensity is 1, 3, 3, 1. We have seen that a doublet gives you equal intensity. A triplet gives you intensity ratio 1 to 1. A quartet is 1, 3, 3, 1, and the 3 is obtained by 1 plus 2, and 3, 1 plus 2. Pentat then is 1, 4, 6, 1, 4, 1. 4 is obtained by 1 plus 3, 6 obtained by 3 plus 3, and 4, 3 plus 1. So 1 plus 4 give you 5, 4 plus 10 give you 10, 4 plus 6 give you 10, 6 plus 4 give you 10, 4 plus 1 give you 5, and this is called a binomial distribution. Here shows some rules for spin-spin splitting. Rule number 1, equivalent protons do not split each other. For example, the first molecule, carbon, have 3 hydrogens that are all equivalent. These 3 hydrogens do not split each other, so you only see 1 absorption line for these 3 hydrogens. In the second molecule, the molecule is symmetric. This is the symmetry line. So all these hydrogens are equivalent, and therefore they don't split each other. Even though they are adjacent, on the adjacent carbons, they do not split each other. So they only show 1 absorption line. Rule number 2, protons that are farther than 2 carbons apart do not split each other. So for the first molecule, the 2 hydrogens are adjacent, they split each other. But the second molecule, the 2 hydrogens are 3 carbons away, so they do not split. Here we show 2 peaks. One is a quartet, one is a triplet. The distance between the peaks is called coupling constant J. J is a measure of the amount of interaction between the 2 sets of hydrogens, creating the multiplet. Rule number 3, 2 groups of protons coupled to each other have the same coupling constant. Suppose this quartet is due to this hydrogen, and the triplet is due to the right side hydrogen. And because these 2 types of hydrogen couple each other, causing this splitting, the coupling constant J to the left side equal to the J coupling constant on the right side. Practice. Propose a structure for a compound C5H12O that fits the following proton NMR data. First, it will be very helpful if we can find out if this molecule contains a double bond, a triple bond, or only a single bond. And this is called degree of unsaturation. For example, if you have a alkene, have 2 carbon, it will have 6 hydrogens. The formula is CnH2n plus 2. Now, if this molecule loses 2 hydrogen, it will form alkene and becomes 4 hydrogen. And alkene, because it has two less hydrogen, it lacks two hydrogen, is called unsaturated. Okay, and for this molecule, the degree of unsaturation is 1. Okay, you lose two hydrogen. All right, it is unsaturated. The degree of unsaturation is 1, and the calculation is use the formula the number of hydrogen of alkane minus the number of hydrogen in the molecule we want to find the degree of unsaturation, and then you divide by 2, because each double bond lose 2 hydrogen. So in this case is 6 in the alkane minus 4 in the compound that we want to find the degree of unsaturation, and then you divide by 2, so that gives you 1. So degree of unsaturation is 1. Okay, now if a molecule contains an oxygen, for example in methanol, note that oxygen replaces 1 hydrogen but also connect to another hydrogen, so oxygen does not have effect on the number of hydrogen. All right, and so when calculate degree of unsaturation, you can ignore the number of the oxygen in the molecule, and therefore in the proposed molecule, to calculate the degree of unsaturation, we calculate first use the number of hydrogens in the alkane that has 5 carbon. For 5 carbon, the hydrogen for alkane is 2n plus 2 according to the formula CnH2n plus 2. So here n is 5. So 2 times 5 is 10 plus 2 is 12. So you should have 12 as your alkane. But this molecule also have 12. So therefore is 12. So this 12 comes from the alkane that has 5 carbon. And this 12 is the hydrogen, number of hydrogen in the molecule we want to find out the degree of unsaturation. So 12 minus 12, and then you divide by 2, because if you have a double bond, it takes 2 hydrogens, and that gives you 0. So that means this molecule does not have degree of unsaturation. It is saturated. It doesn't have double bond, and therefore the only possible is alcohol or ether. You cannot have CO double bond. CO double bond is a ketone or aldehyde, but you don't have double bond, so it can only be alcohol or ether. All right, now let's look at the NMR data. Okay, first it says it has a absorption peak at 0.92 with 3 hydrogens, which is a triplet. So if it's a triplet, that means the neighboring carbon has 2 hydrogen. So you have a 2 CH2 adjacent to this 3 hydrogen. A second peak at 1.50 have 2 hydrogen, which appears as a quartet. A quartet means an adjacent carbon has 3 hydrogen. So CH3 indicates. A quartet means there's a CH3 neighboring to it. And you see here you have 3 hydrogen CH3, 2 hydrogen CH2, and that indicates you have this group CH2, CH3. So these 2 hydrogen appears as a quartet because 3 hydrogen here, and this 3 hydrogen appears as a this hydrogen appears as a triplet because you have 3 hydrogen, and the CH3 appears as a triplet because you have CH2. Okay, again, CH3 appears as a triplet, CH2 appears as a quartet. Yes, so 3 hydrogen. Okay, and so that meets these requirements. And then it says you have a singlet, 6 hydrogen. All right, singlet means the carbon has no hydrogen, and that carbon connect to 6. A carbon has 6 hydrogen, but 1 carbon cannot have 6 hydrogen, so it must have 2 carbon have 3 hydrogen, with a neighboring carbon with no hydrogen, and that gives you a singlet for these two. All right. Now, how many carbon we already have? So 1, 2, 3, 4, 5. The molecule has 5 carbon, so we already have all carbons here. All we need to do is arrange them. All right. One more is you have a peak at 1.64 broad singlet, and that usually is a OH bond, okay, OH group. All right. So how do we arrange them? Okay. So the CH2CH3 probably connect to one of this carbon, CH2CH3, and the OH attached to this side, and that gives you this molecule. Aromatic molecules sometimes give you complex spin-spin splitting patterns. For example, in this toluene molecule, methyl group has an absorption peak at about 2.3. Benzene ring has 3 types of hydrogens, 1, 2, 3, and due to the symmetry, this is also number 1 and 2, so only 3 types of hydrogens. But the proton NMR shows seems to have 2 multiplets, and this is due to the complex spin-splitting of these hydrogens forms overlapping signals. Here shows another example. In this molecule, we have an aldehyde hydrogen which has a chemical shift about 9.7. This peak appears as a doublet. This is because this hydrogen coupled with a vinyl hydrogen, the blue hydrogen. The aromatic hydrogens has a range from 7.5 to 8. If you enlarge this range, you see a doublet. And this doublet is actually due to this green hydrogen or another vinyl hydrogen. This vinyl hydrogen appears as a doublet because it couples with the blue one. So the interesting thing is about this blue hydrogen. This blue hydrogen coupled with the aldehyde hydrogen and also the other vinyl hydrogen, the green one. So it coupled with 2 hydrogens. According to N+1 rule, it should appear as a triplet. But in the NMR spectrum, it has 4 peaks, the blue one, okay, 4 peaks. So instead of triplet, it appears as 4 peaks. So why is that? And this is because the hydrogen, the aldehyde hydrogen and this vinyl hydrogen are non-equivalent. So the coupling of this blue hydrogen with this aldehyde hydrogen has a different strength as it coupled with the other vinyl, the green one. In other words, these 2 coupling have different coupling constant, and therefore you cannot use N+1 rule. All right. So when a hydrogen coupling with non-equivalent protons, N+1 rule doesn't apply. We can use a tree diagram to justify the splitting pattern of this number 2 hydrogen. Okay, first we draw a line to represent the absorption of this hydrogen with no coupling. And now we add these 2 hydrogen one by one. So, for example, let's add number 3 hydrogen first. And from last slide, we know number 2, number 3 hydrogen has a coupling constant 12. So we draw 2 lines with a distance 12. And now we add number 1 hydrogen. All right. And again, from last slide, we know the coupling constant from 2 to 1 is 6. And so each line will split into 2 lines, and the distance is 6. Okay. So from this, we can predict that number 2 hydrogen will have a splitting pattern with 4 lines. This shows an application of proton NMR spectroscopy on a chemical reaction. You should be familiar with this combination of reagent, a borane followed by hydrogen peroxide in basic condition that will add water to a double bond to form an alcohol according to anti-Markov-Nikov rule. So hydrogen goes to the carbon has least hydrogen. Hydroxide goes to the carbon has the most hydrogen. And therefore, the first compound should be the theoretically predicted product. The question now is, can we use proton NMR to confirm this is the product? Or is this possible to form the second product? To answer this question, we compare these two compounds. And we can see that in the second compound, oxygen is connected to a carbon has no hydrogen. All hydrogens are connected to carbon that has no electronegative atom, and therefore all hydrogens in the second compound should appear between 0 to 1.5. On the other hand, the first compound has oxygen connected to a carbon with two hydrogen. These two hydrogens should appear at about 3.5 ppm because oxygen is electronegative. Here is the actual NMR spectrum, and you can see a large 3.5 peak, and this indicates the CH2 attached to hydroxide, and therefore we can say that the reaction forms anti-Markov-Nikov product. Please work on problems from 13.6 until 13.15. If you have 8th edition textbook, that will be from problem 13.13 to 13.22.